Yeah, welcome back. Today we will go much deeper into one-loop superstring amplitudes to see various ideas of the previous lectures at work. So what you saw in yesterday's lecture, we went for one-loop vacuum amplitudes, more or less partition functions, where we needed to look at the states in the string spectrum that could be propagating in the loop. And the main challenge was to organize the infinity of states in closed string spectra to deal with the various oscillators that can be used to create a given state. The easy part was to deal with space-time momentum. This gave rise to a Gaussian integral with the result of inverse factors of imaginary part of tau, which is clearly a modular form. But it was harder to deal with the tower of bosonic oscillators, alpha and alpha twiddle, and to organize those into, well, in case of the bosonic string, into the Ramanujan cusp form. And in the superstring generalization of that exercise, we additionally had to deal with worldsheet spinners, psi, at least in the Ramon-Neves-Schwarz formulation of the superstring that I'm discussing in this lecture series. So for these psi oscillators, well, a small simplification is that these are Grassmann odd variables, so you can excite each oscillator at most once. But nevertheless, it's an infinite tower of these psi oscillators, and as extra complication compared to the bosonic string, they had two kinds of boundary conditions for the fermion field. It may or may not catch a minus sign as you go around the spatial direction of the worldsheet. So this was known as Neves-Schwarz and Ramon sector, these two choices of boundary conditions. Also, Roberto got back to this in his lecture this morning. And the moding of the psi oscillators was half-odd integer in the Neves-Schwarz case and integer in the Ramon case. So in classifying the states in the spectrum, you have to go for these sectors separately. And furthermore, the left and right movers can independently be in Neves-Schwarz or Ramon sector, which means there's a total of 4 options to be, say, in Neves-Schwarz, or maybe in a mixed sector like Neves-Schwarz-Ramon. So we got 4 different contributions to the overall partition function. And well, we just wrote down infinite product representations of these partition functions, and at some point I told you that you get 0. It didn't look like 0, admittedly, and you didn't really have the tool to check that. At best, I gave you an invitation to code the infinite product on Mathematica, then you can check order by order. And today I want to give you some more systematic methods to anticipate such zeros. Yeah, and what was the lesson learned from the vanishing partition function of the one-loop superstring? It was, in the end of the day, telling us that the spectrum is space-time supersymmetric, or at least the number of space-time fermions matches the number of space-time bosons. Namely, we have bosons in the left-right symmetric sectors, namely Neves-Schwarz and Ramon. And we have space-time fermions in the off-diagonal sector, namely Neves-Schwarz/Ramon and Ramon/Neves-Schwarz. And let's say the positive and negative contributions to that superstring partition function could be identified with the number of bosons and the number of fermions, respectively. And we did subtract them from one another in the partition function just to incorporate the old school QFT wisdom that fermions in the loop contribute with opposite sign compared to bosons in the loop. Yeah, since the end result for that partition function was 0, it was not a big deal that it is compatible with modular invariance, but I promise that today you will get non-zero quantities which are compatible with modularity. So maybe this is a concrete motivation to now do one-loop amplitudes with a non-zero number of external legs. So I will go into detail how to compute that gadget and what the integrand with respect to the moduli space M1 semicolon 4 is. Yeah, and in order to get there, I want to start by introducing a toolbox to represent the ingredients for that integrand here. So in the end of the day, you will need a correlation function on the torus, similar to those that you saw in Roberto's lecture. And yeah, the building blocks of these correlation functions, well, in the end of the day, they are bound to be Jacobi forms, because by this principle of modular invariance, in the end of the day, it shouldn't depend on which fundamental domain of SL2 you choose. So eventually, we will represent all these correlator building blocks in terms of Jacobi forms. However, it's quite a bit of a way to get there. In intermediate steps, it doesn't look particularly like Jacobi, but in intermediate steps, we find quasi-periodic objects. I mean, Jacobi forms are functions of z and tau, where z can be any of these marked points, and by definition, Jacobi forms are doubly periodic. But as I will detail in intermediate steps, not everything is doubly periodic, which you find in these correlator computations. And worse than that, intermediate steps will also be non-modular. Okay, so what are these not optimized objects that I'm bad-mouthing here? These are so-called theta functions, sometimes called Jacobi theta functions, but I shouldn't use that term because it's potentially confusing. Theta functions are not Jacobi forms. Okay, and the way I will present them, you will meet 4 flavors of theta functions at genus 1. And let me stress, this is something you get in intermediate steps. And it's important to walk the extra mile to eventually combine all the theta functions to be honest-to-God Jacobi forms, such that you manifest the properties that you would like to see from an endpoint correlation function on the torus. Yeah, so this is the roadmap for today's lecture. And let's go straight into the definitions of the promised theta functions. So maybe on the positive note, these are meromorphic functions. So no need to worry about appearances of z bar or tau bar. And above, yeah, you see infinite product representations. If you take a closer look in how the z dependence and how the tau dependence occurs, well, maybe easiest to note is the parity properties as you reflect the mark point z. Namely, all the infinite products are by construction symmetric, undergoing from z to minus z. So the only source of non-symmetry is the sine and cosine in case of Jacobi theta 1 and theta 2. Okay, so only the sine function is in fact antisymmetric. So there's a single theta function which is odd under z goes to minus z. This is theta 1. You will see theta 1 on a more special footing than the others. Yeah, and the remaining theta 2, theta 3, theta 4, they turn out to be even under reflection of z goes to minus z. Okay, now a first reason to be happy about these definitions is that the partition function from yesterday, or its individual constituents, can be rewritten in terms of those. Of course, there was not a z yesterday, so let's just look at the z equals 0 version of the above and see how yesterday's results can be repackaged. And maybe I should give you yet another infinite product, namely the Dedekind eta function, which is, roughly speaking, a root of the Ramanujan delta. Well, I wrote for you 2 lectures ago that delta 12 is 24 powers of 1 minus q to the n, infinite product over those. And of course, I can do this without the 24th power. and simply go for that one. Okay, so with the definition here and there, we can go back to the various oscillator sums from yesterday. So these were essentially traces over Q to the power of L naught, the Virasoro generator. And yeah, I used various calligraphic H's as a notation for the subspaces or factor spaces where you only excite a certain species of oscillators. So here we were only looking at the bosonic oscillators alpha, namely the left movers alpha as opposed to the right movers alpha bar. And yeah, we saw that you get geometric series for each space-time direction, so that geometric series was putting down this infinite product into the denominator. So that's why you get eta to a negative power. And in light cone quantization, we had 8 space-time directions where the oscillators contribute non-trivially after solving the BRST constraints. Good. And well, since we really isolated the alpha oscillators, we want to get something with integer powers of Q. And sometimes this funny Q to the 1/24 can be inconvenient. So here, for instance, I need to compensate that by hand. But the good thing, these free-floating powers of Q will disappear once I combine the alphas with the psis appropriately. So with this intermediate step, we can repackage the combination of alpha and psi oscillators in a nice way. So let's start in the Navier-Schwarz sector. So this symbol here, H Navier-Schwarz, was in fact doing the GSO projected Navier-Schwarz sector. Remember, GSO projection meant we need an odd number of psi oscillators, an odd number of worldsheet fermions, which is a neat way of projecting out the tachyon. But more importantly, in the bigger scheme of things, GSO projection is a ticket for modular invariant partition function, modular invariant amplitudes, and also for the CFT experts for locality of the operator algebra. Okay, so this is going to be GSO projected, and the result had 2 types of infinite products, some of them with oscillator contributions 1 plus Q to the oscillator number. So this 1 plus Q to the oscillator number and for half-odd integers can be found in the theta 3 function. So if I don't know yet about GSO projection, I should log in the theta 3 function. Imagine setting z equal to 0, and then it's the first 2 factors in theta 3 which give us the desired infinite product for the psi half-odd integer oscillator. And strictly speaking, each theta 3 has 2 of them, namely 2 places where we need to set z equal to 0. Which means each theta 3 takes care of 2 space-time directions. And since there are 8 in total, we need 4 powers. Okay, so up to now, it seems like I didn't really care about GSO. Now it's time to also look at the fermion number insertion. So the net effect of putting in the -1 to the fermion number is that you get a minus sign in the 1 minus Q to the oscillator number. Now this is time for theta 4, where the minus sign coming from the -1 to the fermion number. And once more, each theta 4 has 2 such factors of 1 minus Q to a half-odd integer. And so once more, in view of the 8 space-time directions we want to cover, we need 4 powers of theta 4. Okay, so this was the meat of dealing with the psi oscillators in the Navier-Schwarz sector. But there is still a little bit of extra luggage, which theta 3 and theta 4 bring. There is this terminal factor, 1 minus Q to the n. So those, of course, need to be compensated. And here I'm already combining with the alpha oscillators. So there are various sources of Dedekind Ada, and if the dust settles, you find 12 powers of Dedekind Ada downstairs. Okay, and the last nifty detail was that due to vacuum energy or due to the tachyon occurring at mass level -1, we also need this little prefactor, as commented on yesterday. Good, this is the most compact way I know of how to do the state counting exercise in the Neveu-Schwarz sector. And there's a pretty similar formula in the Raman sector. Here the main difference is that the oscillator number is integer, so then it's the theta2 function which will do the job. The theta2 function has these numerator contributions 1 plus q to the integer. So just look at the two terms which have a z dependence and set z equal to 0 once more. Okay, so you get theta 2 to the power 4, again power 4 because we need to cover 8 space-time directions, and once more there is a little bit of Dedekind Ada bookkeeping to be done, and you once more have 12 powers. Yes? 1 over square root 2. Where is the square root? Square q, this one? Mm-hmm. Yeah. Both theta 3, yeah. I think you're mixing two things that shouldn't be mixed. Okay, there are two statements. Let me start with the technical one. The interplay between those two terms cancels the Q-independent piece. Both of them start with 1 plus dot dot dot, but they cancel between theta 3 and theta 4. And this cancellation is eventually the removal of the tachyon, because the term 1 plus dot 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 is lowest order in Q. And at lowest order in Q, I have the tachyon. But the tachyon is, strictly speaking, at a mass level of -1/2. And this is statement number 2 that I want to unmix. Statement number 2 is, since the lowest mass level is a negative one, we must reflect this in the Q expansion. Mass level k should occur with q to the power k, even if k is negative. Concretely, the would-be tachyon is at k equal -1/2. So the tachyon contribution which cancels is obliged to appear with the power of q to the -1/2. That's why I'm putting this here. So this is the elaborate reason, and there's also a lazy reason. Put q to some unspecified power alpha, and alpha equal -1/2 is the only choice consistent with modular invariance. Okay. Yeah, what I didn't get to say is also be careful about the factors of 2. We start with an 8-fold degenerate Raman vacuum. So there is initially an 8 in the numerator, but the normalization of theta 2 will at the end of the day leave you with this. Good, so this is a slightly more compact way of writing yesterday's result, and also this overall upshot with a space-time supersymmetric spectrum is most neatly written as a theta function identity. So the key to the vanishing partition function was that already these chiral blocks, which take care of the psi's only for the left movers, that these chiral blocks already vanish. And yeah, with these new toys on the board, you can now expose this vanishing by saying that take 4 powers of theta functions 2, 3, 4, combine them with minus signs like such, and this is 0. Okay, so this is a famous theta function identity known under the name Jacobi's abstruse identity. And yeah, my apologies that I won't be proving it in front of your eyes, but if you want to know where it comes from, you need so-called Riemann identities among theta functions, among quartic expressions in theta functions. I will quote and use them again towards the end of the lecture, and I would recommend all of you to take a look at Riemann identities in the references I gave or your favorite other resource. Yeah, you can think of this as morally a theta function upgrade of a trigonometric identity like sine square plus cosine square equal 1. Okay, so this is a zeroth order application of theta functions. Ignore their z dependence, set z equal to 0, and then with the theta constants, you can already have a good time expressing the partition function. Now it's time to switch on the z's. So again, the next goal is to handle correlation functions on the torus. And now it's important to check what the theta functions do under A cycle and B cycle shift. So here, this is about the quasi-periodicity properties. And I'll take the liberty to present this in a table format. So start with the theta functions at z and tau as defined on the other board. And here, I want to give you the results first under an A cycle shift, go from z to z plus 1, and also the result of a B cycle shift, z goes to z plus tau. And yeah, as I was announcing, this is not quite working out. Let's say the most blatant departure from being doubly periodic is coming here in the B cycle shift. So maybe this is the biggest shock that you will see in that table. You get, first of all, a phase that depends on, whoops, this is a typo, that depends on both arguments, z and tau. And there's also a minus sign, which is potentially less disturbing than that phase. So it's because of that phase here that the theta functions are called quasi-periodic. I mean, the consolence prize is that you get the theta function back, but on top of that, there is all that noise coming from here. Yeah, and actually, this noise is shared by all the 4 theta functions if you go around the B cycle. So this is a kind of pain conservation in going from one theta function to the next. But what does change from one theta function to the next is the accompanying sign. So there was a minus in case of theta 1, and that minus sign is shared by theta 4, but it does not occur for theta 2 and theta 3. So the fine print in distinguishing one theta function from the other is in this profile of plus and minus signs. Now, as we go to the A cycle shift, so here there is no analog of that disturbing phase. So the periodicities are cleaner for the A cycle. And the only non-trivial effect of A cycle shift is a selective minus sign. Again, 2 theta functions do have a minus and 2 other theta functions don't. And now if you look at the pattern of pluses and minuses, then all choices of putting a plus minus sign here and a plus minus sign there are realized. So disregarding that phase, you can say that for each plus and minus choice under A cycle and B cycle shift, there exists one theta function which realizes it. Okay, so these are the quasi-periodicities of the theta functions. This is now your last chance to take a blackboard photo if you want to keep the definitions. No smartphones coming up, then I can erase. Now the next property of theta functions I want to gather is their non-modularity. And yeah, also here, they are not as tidy as we would like them to be. I mean, the goal is to eventually express correlators in terms of Jacobi forms. And let's see how close these theta functions come to delivering the modular properties of a Jacobi form. So now there are again two moves to consider, but now moves on the variable tau. So here I want to go through the two generators S and T of the modular group SL2Z. Remember that it's sufficient to study the behavior under S and T, and then for an arbitrary SL2 transformation, SL2Z, you can represent them as a word of finite length in S's and T's. Okay, and actually about the modular S transformation, we discussed that also the first argument Z needs to be transformed along the way. For instance, this is the only way of enforcing that the A period is 1, either before or after modular transformation. Okay, so what do we get here? Maybe you can anticipate from the powers of Q that were on that board before. There was a Q to the power 1/8 in case of theta 1 and theta 2. And yeah, as you do this tau goes to tau plus 1, you're of course sensitive to fractional powers of Q. So that's why you have an 8th root of unity coming into the modular T transformation of theta 1, and likewise for theta 2. Now, the theta 3 and theta 4, maybe you remember seeing half-odd integer powers in Q. So you could wonder if there are minus signs coming here, but not quite. Theta 3 and theta 4 doing something more amusing under modular T transformation. They just swap. They are mapped into one another. So this is something which you saw in Roberto's lecture under the name vector-valued modular form. If there's more than one object, and under modular transformations, you produce permutations. Okay, so here is a concrete realization of that. And if we now look at the modular S transformation, yeah, maybe I start with the vector-valued aspects of that. So theta 1 is somehow decoupled, but modular S transformations change between theta 2 and theta 4. So now the non-trivial permutation acts on theta 2 and theta 4. Whereas theta 3 is some sort of a fixed point. I'm saying some sort of because there are now again a couple of more unpleasant factors which are morally the analog of that. So what is this extra junk here? So the modular S transformation produces some phase which again depends on both Z and tau. Yeah, it's disturbing, but it's at least the same for all the 4 theta functions. And then there's some more stuff happening. Namely, there is some power of tau, a square root of tau. You could be tempted to say, it smells a little bit like modular weight a half. And okay, if you choose good combinations, then they indeed behave as if they had modular weight of a half. But only do this in suitable combinations. For instance, there is an obvious Pandora box about which branch of the square root should I choose. Yeah, you have good reasons to be worried about these in isolation, but we will fortunately see that all the theta functions combine in good ways, such that we never have to scratch our head about a branch choice for the square root. Yeah, all this to say, theta functions are good intermediate objects. They are meromorphic, but they are not yet optimized to be Jacobi forms themselves. They fail to be Jacobi forms both by their quasi-periodicity and by their, well, not quite modularity. Yeah, so that's all I wanted to say about theta function preliminaries. And now I would go to the actual correlation functions on the torus. Any questions before we proceed to torus correlators? Yeah. Ah, yeah. Yeah, maybe it's easiest if you wait for the examples and then you can ask me again if you want to hear more about the overall pattern. Logarithmic derivatives are, for instance, very nice. Okay. Yeah, so now this is about torus correlators. And yeah, the specific elementary fields whose correlation functions I want to study, these are the worldsheet boson, x mu, and likewise the worldsheet spinor psi. So as you can see from the choice of alphabet for the indices, I'm already forgetting about the light cone. So here I'm presenting things covariantly, where mu and lambda run over all directions of Minkowski spacetime. Good. Yeah, for both of them, for both x and psi, we need some mechanism to construct two-point functions at first. And we will start with the boson. So the two-point function, I will also call it the Green's function or green function. And to make sure we are not carrying around these Lorentz indices forever, let me define this by little g, the scalar part of the two-point function. Let's also strip off some alpha primes. Okay, so all the dependence on the moduli z and tau is sitting in the object that I'm calling g. And now, what is a good choice for this bosonic Green's function g on the torus? Yeah, there are a couple of principles that fix it almost uniquely. And oh yeah, this is a good point. Maybe I want to stress that being on the torus, there's translation invariance for the last time on the torus. So the correlation functions will only depend on the differences of points. So if I have an n-point function, then the right-hand side is a function of n minus 1 differences. Thanks a lot, Daniele. Okay, so what are the principles that fix the Green's function for us? One is that the short distance singularity should be the same on arbitrary genus. And specifically, the two-point function of the boson on the sphere is a logarithm. This would be the analog of g if we were on the sphere. So I should present something which has the same short distance behavior when z and w are close to each other. And there's a very fancy way to telling you about a logarithmic short distance behavior. If I take the Laplacian in z, like del z bar z, then I get a delta function. So this is a way of packaging the information on the short distance behavior. The Laplace equation should better have a delta function or delta distribution enforcing z equal w. So with this, we have automatically obtained that. But now, we are on a compact Riemann surface. We have a total derivative here, and total derivatives should better integrate to 0 if this is a single-valued function. So imagine you were to integrate that differential equation over z. You want 0 integral on the left-hand side, but non-zero integral of the delta function on the right-hand side. So this cannot be the end of the rope. We would currently violate the expectations on an integral over a Laplacian. So you need one extra term, which is the inverse volume of the torus. So this term ensures that also the right-hand side integrates to zero. So to ensure that this Laplacian integrates to zero over the torus. Good. So this Laplace equation, in summary, it comes about by insisting on the short distance behavior known from the sphere, and then posing some sort of consistency condition with how a Laplacian should integrate. I'm in between the lines using single-valuedness. So even though I haven't told you yet what G is, it should better be doubly periodic, and total derivatives only integrate to zero when there is a single-valued function in the game. Okay, so this is already a wealth of information on G, but I haven't fixed the zero mode yet. Imagine you were to add a constant, your favorite function of tau, adding that. Then it still solves the Laplace equation. So we have a joker. We can dial the zero mode to more or less whatever we like, and we don't affect the Laplace equation. And the choice I would recommend is dial the zero mode such that the Green's function itself integrates to zero. So again, we integrate over the entire torus. So imagine you find a random solution here where the Green's function does not yet integrate to zero. Then just add a constant to it. Dial the constant to add such that the redefined Green's function integrates to zero. Okay, so these are basic requirements on the bosonic Green's function. And now it's time to lift the secret, how to realize all of that. And I should also spell out the additional requirements that were in between the lines. We now need an explicit solution to the Laplace equation, to the zero mode condition, and finally it should be single valued or doubly periodic, single valued on the torus. And furthermore, may sound like a tall order, but I furthermore want it to be modular invariant. So it's really a great deal of properties. I hope none of you is doubting whether such a gadget exists. So the solution to all of that is given by, we essentially repackage theta functions in a good way. Oops. We realize the short distance behavior by feeding the logarithm not with z minus w, but with theta 1. Theta 1 is the only odd theta function, so it's the only one which at the origin behaves like z. So more precisely, if I Taylor expand around the origin, I get z times a constant, a constant with respect to z, plus order z cube. So this is definitely good enough to reproduce the log mod z square behavior of the Green's function on the sphere, or the desired delta distribution in the Laplace equation. Now, you can start checking out the double periodicity, and you can also look at the modular transformation. And here you will indeed have a bit of trouble. Look at the right column, what theta 1 does under the B cycle shift. There is this phase e to the minus 2 pi I z minus I pi tau. So this is not ending well if I do a B cycle shift of that term alone. So we need help from yet another term which has the opposite B-cycle shift. And it turns out that this addition here does the job. Imaginary part of z square divided by m tau. So also this one has a non-trivial B-cycle shift. But the A-cycle transformation is all right. Under the A-cycle shift, theta 1 picks up a minus sign, but the absolute value square flattens out that minus sign. So the first term is good on the A-cycle shift. And indeed, this extra term, it's unaffected by A-cycle shift. It's the imaginary part of z, which doesn't change as I send z to z plus 1. Yeah, so for these reasons, this is a good choice of Green's function. And what is perhaps least obvious is whether it integrates to 0. I mean, checking this is a bit more work, but the Dedekind eta function downstairs is the one which ensures that the Green's function integrates to 0. Okay, so with all of these fine-tunings, the result is indeed single-valued. And it's modular invariant in the sense of being a Jacobi form of weight 0, 0. Yeah, so this is the bosonic Green's function to use. And okay, as to the modularity, well, in principle, we could jointly try to show that this is modular invariant. I mean, you see the properties of the theta 1 function. But an even nicer way of checking the modular properties is to do a Fourier expansion in Z. So this will manifest. Oh, and it will also manifest the double periodicity. Okay, so we are periodic under Z goes to Z plus 1. And we are furthermore periodic under Z goes to Z plus tau. Which means that if we go back to the beloved co-moving coordinates, u and v being real, then we have periodicities under u goes to u plus 1, and likewise v goes to v plus 1. So we can do Fourier expansion in both. This is something that I already illustrated yesterday when we looked at examples of Jacobi forms. I think we had these Zagier single-valued elliptic polylogarithms on the board. And indeed, the Green's function is a particular example of that. We can Fourier expand in both u and v, these two co-moving coordinates. And we need integer appearance in a plane wave with integers m and n. And now the Fourier coefficient for a given combination of plane waves is something like 1 over momentum absolute value square. Okay, and now this is very good to check the modular invariance. I mean, you saw it already for the holomorphic Eisenstein series. These lattice factors m tau plus n transform nicely under SL2Z. And okay, you need to work a little bit to check the modular transformation of the plane waves. But yeah, this is maybe a more inviting presentation to check modular invariance. But yeah, this representation also manifests the double periodicity. And it even manifests the fact that the Green's function integrates to 0. Simply because integrating over the torus picks up the 0 mode with respect to both m and n in this double Fourier expansion. But concerning 0 modes, well, we explicitly rule out the m, n equals 0, 0 choice. Of course, we had to do that, otherwise this would blow up. But yeah, by the lack of 0 mode, the Green's function indeed integrates to 0. Okay, that's what I wanted to say about bosonic Green's function. And I will next do the fermionic analog, unless you want to ask a question about this now. Okay, let's go for the worldsheet spinners. And we were already noting yesterday that there are different boundary conditions, Neveu-Schwarz and Ramond. So these were primarily coming from here. What does the spinner do under a cycle shift? Z goes to Z plus 1. But then you heard from Roberto in the morning that there's also a boundary condition in tau, which is controlled by fermion number insertion in a trace. And so here there is a second possible source of plus or minus sign, going around the B cycle rather than an A cycle. And importantly, these two signs can be chosen independently. So there is a 2 by 2 array of choices for these two minus signs. Okay. So we look at 2 by 2 different boundary conditions. And one of them is a bit special, namely the odd choice. Let's assign number nu equal 1 to the choice when you have plus and plus in both cases. Oh yeah, also that was covered by Roberto. If I allow plus and plus, then there is room for a fermionic zero mode. So a zero mode is obviously periodic in any way you may go. So only if I choose plus and plus, the spinner can have a fermionic zero mode. Yeah, this is more special than the others. And actually, in amplitude computations, these zero modes will, at the end of the day, require a saturation. We need to insert a psi into a correlation function for each zero mode. And doing things covariantly, there are 10 spacetime dimensions, so you need to saturate 10 zero modes. That doesn't occur prior to 5-point scattering amplitudes. And when it occurs, then it comes with a Levi-Civita symbol, because these 10 zero modes appear antisymmetrically with respect to their Lorentz indices. So this is more special than the rest. It will give you parity odd amplitude contributions because of the Levi-Civita symbol that is generated by the zero mode integral. And for all of these reasons, I won't discuss it. Since the main discussion is about the 4-point function, this is not giving you enough psi's that you could saturate all these zero modes. So that is my main excuse for not covering these parity odd terms and this choice of boundary condition. Then let's look at the other 3 choices, which I do discuss and will need for the 4-point function. So the remaining 3 choices are said to be even. And I assign numbers 2, 3, and 4 to these other choices. So in terms of these pluses and minus signs over there, these are those which go like that. And with all these definitions of theta functions, I can give a unified treatment for all of these 3 even boundary conditions. So a 2-point function equipped with these even boundary conditions nu can be written in terms of theta 2, theta 3, theta 4. So essentially, it's this. Oh yeah, and there's furthermore a ubiquitous theta 1 involved. So this is the unified expression for the three two-point functions associated with nu equal 2, 3, or 4. And I'm again outsourcing the Lorentz indices. So let's introduce the Sego kernel S nu. By translation invariance, we put the difference, z minus w, into the first argument. And here the second line tells you what this scalar object is. So this is the so-called Sego kernel, or fermionic Green's function. Okay, how can I justify that this is a good choice? So once more, we need to reproduce the short distance behavior known from genus 0. And indeed, there is a theta 1 downstairs. So it's this theta 1 downstairs which gives rise to 1 over z plus something which is regular as z and w come together. Whoops, hope this is halfway readable. And the residue of that pole is 1, because first of all, there is an inverse derivative. Whoops, maybe I should say that those two together have a simple pole with residue 1, and at the residue of that simple pole, you lose the dependence on theta nu. Okay, short distance behavior works, and now the global properties need to be worked out. The A cycle and B cycle shifts should be compatible with the plus and minus sign arrangements here. And this is where you use the periodicity properties of the theta functions, which are unfortunately no longer on the board. But you probably remember that I complained about a universal phase factor that went like e to the minus 2 pi iz minus I pi tau. And these disturbing phase factors drop out, because there's one of them in the numerator and one of them in the denominator. So the only thing left under a B cycle shift is the plus minus sign. And the A cycle shifts of theta functions were individually neat, and again, there is at best a minus sign that you can catch. Yeah, perhaps before we go into the break, I just give you an overview of what this plus-minus sign arrangement is, and to justify why I associated values nu equal 2, 3, 4 with these boundary conditions. So let's check the plus-minus periodicities. Okay, we need to worry about nu equal 2, 3, and 4. So let's do a cycle shift. And by just plugging in the behavior of the theta functions from a couple of blackboards ago, you will find that you get plus sign, minus sign, minus sign. And in each case, you reproduce the same species of Sego kernel that you started with. No permutations on nu here. And yeah, for the B cycle shift, the plus-minus sign arrangement was slightly different in the table from before. And as a consequence, you get something different there. And now this is the justification why I claimed above that nu equal 2 gives you plus and minus. So it is these pairs of pluses and minuses that you can see over there, and which help you to prove the claim over there. Yeah, so again, the A-cycle periodicity tell you whether you are in the Neveu-Schwarz or in the Raman sector. So this S2 positivity on the A-cycle shift is hallmark of Raman sector. And catching a minus sign here in case of nu equal 3 and nu equal 4 means Neveu-Schwarz sector. And the other boundary condition for B cycle shift, this was checking out whether there is a fermion number operator insertion or not in the underlying trace. And yeah, as Roberto confessed, it's a bit counterintuitive. It is the case with the plus sign, where you have an extra -1 to the f. Fermions are weird, and hence fermions without insertion of that have a minus sign as a boundary condition under z goes to z plus tau, which comes in one way or another from the anticyclicity of the trace. Good. This concludes the discussion of the periodicity properties. And I can't help telling you also about the modularity properties. In the end, we want to use these building blocks to engineer correlation functions with good modular behavior. So we should also work out the action of the T and S generators of the modular group. And once more, you can start with the behavior of the theta functions and plug it in all of the ingredients of the Sego kernel. And what you then find is that also the Sego kernels are vector-valued modular forms in the sense that you get non-trivial permutations. And these are on the nose, the permutations that we saw before for the theta 2, theta 3, theta 4. So if you compare with the earlier table, you had exactly the same swap of theta 3, theta 4 under the modular T transformation. And there was an analogous swap of the theta 4 and theta 2 if we do S transformation instead. But a little extra is that there's furthermore a factor of tau. Okay, yeah, this can be traced back to these square roots of -I tau. Yeah, perhaps this is a good moment to answer your question. What combinations are good? I think ratios of theta functions are typically good, because then you lose the annoying phase in the B cycle shift, and furthermore, you are balancing out these square root -I tau factors under the modular S transformation. And apart from ratios, also logarithms of absolute value appears to be good, provided that you do the doubly periodic completion. Yeah. So these are maybe two different mechanisms how you build a good Green's function, where you compensate for the flaws of individual theta functions in different ways. Yeah, this completes what I wanted to do about the two-point function, and maybe we do the rest after the break. Okay, I hope there was enough time for any combination of coffee and restroom visit. Let's go back to the goal of assembling the correlation functions for one-loop scattering amplitudes. As a first step, we looked at two-point functions of both worldsheet bosons X and worldsheet fermions psi, where in the bosonic case, the Green's function is up there, essentially a logarithm of theta 1, plus a doubly periodic completion. And in case of the spinors, we have the Sego kernel as a two-point function, a simple pole with some good periodic completion. And what I forgot to highlight was that the psi field is essentially chiral. I mean, if I don't put a bar over here, this is the top component of the Dirac spinor on the worldsheet, and on its equations of motion, that's meromorphic. And that's why you also see a meromorphic two-point function. Whereas the field X, as long as I don't take any derivatives, it's completely non-chiral. X has both alphas and alpha bars, and that's why the bosonic Green's function is real. And okay, admittedly, if you take its derivative, it's not fully meromorphic, but that's the fault of the zero mode, the space-time momentum essentially, which is the shared zero mode between del z of x and del z bar of x. So you can view this doubly periodic completion as coming from the zero mode integral of a space-time momentum. Good. But now what I wanted to discuss next is how to combine these spin structure dependent fermionic two-point functions with the oscillator sums from before. And yeah, that combination is pretty intuitive. In assembling the moduli space integrands of one-loop superstring amplitudes, you democratically go through all these boundary conditions of psi, and for each boundary condition, you combine these non-vacuum correlators, which were indexed by nu equal 2, 3, and 4, with the above oscillator sums. And perhaps I should introduce a better notation for these oscillator sums. So before we looked at a quantity which was z psi, and well, which vanished at the end of the day. But now the new feature is I now want to refer to the individual contributions and weight them with different psi correlators. I mean, this sum here vanishes if I keep the nu equal 2, 3, 4 sectors as they are, but you will get non-vanishing contributions if I put here some Sager kernel, there some Sager kernel at nu equal 3, and there some Sager kernel with nu equal 4. Okay, and a good convention to do all of this neatly is to organize the oscillator sums like that. It's not on the nose, the normalization you saw before, but it's off by a factor of 8 pi to the 4th, which I'm introducing here for cosmetic reasons. And if you really want to see it in terms of the Dedekind Ada function, you can, of course, roll back to this one, and then it should look like the formula you saw earlier in the lecture today. Okay, so for all future references, this is what I mean by Z nu, the oscillator sums, or the individual contributions to the partition function, given a choice of boundary conditions for psi. And yeah, similar to before, we will be interested in the modular properties of that. Given that it no longer depends on Z, it's obsolete to speculate about periodicity properties. So the only thing to check is the modular behavior of these oscillator sums or partition functions. So we proceed with the same table as before, that here's one column for the modular T transformation and yet another column for the modular S transformation. And once more, you can work them out by knowing about the modular properties of the theta functions. So here we need the simpler modular properties when Z is set equal to 0. And yeah, to improve on the service factor, I also spelled out the modular properties of this theta prime at the origin. I don't think you had all the formulas to assemble that, so maybe copy-paste also those into your database of identities. Yeah, I mean, this derivative of theta prime at the origin is essentially the third power of the Dedekind Ada function, or the 8th square root of the Ramanujan-Cusp form. Yeah, but I was about to give you the entries of this table. And well, if you remember what the Sager kernels did under modular transformations, then I don't think that this table will have any surprises for you. We already noted that these theta functions, or powers thereof, are a little bit like vector-valued modular forms and permute non-trivially. And we have exactly the same permutations for the oscillator sums Z that we noted for the Sager kernels over there. So this is really in perfect harmony, going between Z and Sager kernel S. Under modular T transformation, 3 and 4 are mixing, and under modular S transformation, it's 2 and 4 who mix. And the only fine print that is a bit different is the power of tau. So modular transformation is not only giving you permutations, but furthermore the usual automorphy factors C tau plus D. So here this was modular weight 1 with the first power of tau. And over here for the oscillator sums, we formally have modular weight minus 4, apart from this permutation here. Okay, so it's good to have all these formulas spelled out here, but it's also useful to make a central conceptual point once again. GSO projection is there to be modular invariant at the end of the day. So remember, GSO projection was giving you a linear combination of theta 3s and theta 4s. So the theta 4s are introduced by the presence of this fermion number operator within the GSO projector. And it's really important to have both of theta 3 and theta 4, otherwise you wouldn't close under the modular group. Then these permutations wouldn't work out. So GSO projection is not a cheap way of removing tachyon, but an essential ingredient to have modular invariance. And furthermore, modular invariance orders the Raman sector. If you were to not include Raman sector, then you would have a problem with the modular S transformation over here. So this construction of the superstring spectrum and the associated contributions to one-loop amplitudes, this is all a fine-tuned system where you shouldn't fiddle around much. It's so easy to lose modular invariance. Okay, so this is how you should combine these fermion correlation functions with the corresponding oscillator sums from the vacuum amplitude. And okay, now up to here, you've only seen 2-point and 0-point functions. So maybe some of you are getting impatient. What about higher multiplicity? So here is a concluding comment to also cover higher point correlation functions. And why is it all done with a small comment? Higher points is quite easy because we have a free field theory. We have a free boson and we have a free fermion. I didn't give you the respective worldsheet actions, but they are quadratic. It's essentially x Laplace x and psi del bar psi. So they have quadratic worldsheet actions and are therefore said to be free field theories, which means the correlation functions can be computed from the Wick theorem, that in a higher point function, I just sum over all possible pair contractions, all possibilities to pair the fields and contract using 2-point functions. So all this to say, knowing the 2-point function is enough, or at least with some basic combinatorial insight on how to use the Wick theorem. So the 2-point function is good enough to nail the 2k point function, because these 2k point functions boil down to products of k 2-point functions. So you just iterate the expressions for the bosonic Green's function and the Sego kernel from before. So 2 concrete examples of that. Suppose I have a 4-point function of psi. The 4-point function means this will be quadratic in Sego kernels. And I will actually use this 4-point function as an excuse to introduce normal ordering. Now I forgot whether you saw normal ordering colons in Roberto's lecture. Okay, so normal ordering colon means that I don't create any 1/0. So why do I fear of 1/0? If you were to take a 2-point function of the 2 coincident psi's, this is not ending well. And everything that the normal ordering colons do is forbidding you certain 2-point functions. So you don't apply the Wick rules to 2-point functions of fields that are in the same colon environment. So concretely, you don't contract the first psi with the second psi. And instead, the Wick contractions you can do is between the first and the third, and likewise the first and the fourth. So there are two inequivalent Wick contraction patterns, and accordingly the Lorentz indices will get antisymmetrized as shown here. Yeah, and the dependence on Z, W, and tau is just entering through a square of the Sego kernel. Yeah, this is going well with 4 fields, and it keeps on going well if there's an even number of fields, even if there is an exponential full of even numbers of fields. So a next application of Wick, admittedly, this is quite a jump in difficulty, but yeah, we can talk offline about how to deal with such exponentials. So I'm exponentiating the field X. But it's a free field, so it's not too bad. So what you effectively do is exponentiate the two-point function. So what you get from here is an exponential over two-point functions, and you feed the two-point function with all pairs of points. So all the zk minus zl will end up in the bosonic Green's function. And of course, there is some non-trivial Lorentz index structure to the two-point function, which will just produce Kroneckers on the space-time momenta. So you get all these contractions here between space-time momenta. Yeah. So don't allow the exponentials to scare you. It is nothing but Wick over and over again. Okay, so this is why most of the discussion is about the two-point function, and having the two-point function under control, you get the endpoint function almost for free, modulo the content of that board. Okay, I think all the preliminaries are there to directly attack the one-loop four-point function of massless states of the type 2 superstring. So we look at 4 massless closed string states, which strictly speaking cover the entire supergravity multiplet if you do the calculation supersymmetrically. But since I'm using the RNS formalism, you don't see all of the fermionic components. It is mostly the 4 graviton component which I'm computing for you. And the result is the same whether I'm in the type 2A or in the type 2B theory. So for gravitons or other Navier-Schwarz states, I need to go all the way to 5 points to see the difference between type 2A and type 2B. So for the experts, it's the parity odd sector which feels the difference between the type 2A and type 2B theory. But not so at 4 points. So that's why I didn't put an A or B into the headline of this section. Okay, you heard it a couple of times before. One-loop amplitudes are integrals over the moduli space of tori with n marked points. And clearly, moduli space of tori contain integral over the fundamental domain of SL2Z. And then a good choice of coordinates for m semicolon n is to use tau together with the marked points, z2, z3, ... zn. I start with z2 because I have translation invariance as a joker. I will set the first marked point to the origin without loss of generality, and it means it's sufficient to integrate over 2, 3, and 4 if we are in the 4-point function. And all of those are integrated over the torus. Okay, so maybe you are wondering why I'm distributing the im taus in the way I do. So first of all, this is hopefully consistent with the Gaussian integral over spacetime momenta. We noted before that integrating over spacetime momenta gives 5 inverse powers. So I just distributed these 5 powers over the integration measure to make them individually modular invariant. So maybe that's almost a spoiler, but yeah, I have engineered both integration measures here to be both modular invariant. Okay, so far so good. No issue with the measures. Now, I haven't really told you about the systematics of putting external states on the worldsheet. In a full glory discussion, I would be introducing so-called vertex operators, certain conformal primary fields which take care of a state insertion on an arbitrary Riemann surface. And what these vertex operators always encode is spacetime momentum. There's always an exponential of p dot x inside a vertex operator to give spacetime momentum to a given state. So this example here is really ubiquitous in all, string amplitudes of arbitrary genus. Just make sure you use the appropriate Green's function tailored to the surface under investigation. So I'm just copy-pasting this exponential of Green's functions from over there. And I'm furthermore introducing dimensionless Mandelstam invariants because we will deal with these dot products of momenta over and over again. Yeah, so the definitions baked in here are minus alpha prime over 2 dot product of momenta. And as you can imagine, also these differences deserve a shorthand. This is Zk minus Cl. Good. This takes care of the worldsheet bosons and the way they appear in the vertex operators, at least within the scope of the 4-point function. Now, after the bosons come the fermions, and okay, this requires a little bit more care to deal with the fermions. Let me just say first and foremost that there's a factorization into left and right movers. So whatever the fermions do, I only need to worry about the left movers, and once I have simplified the left movers' contribution to death, then I will copy-paste the result and also simplify the right movers with the same method. So let's only worry about psi and forget about psi bar for the moment. Good, so what is hidden in this mysterious factor of C for the chiral blocks? So this C refers to a chiral spin structure sum. This C, I guess I was almost saying that before, you need to look at all the possible boundary conditions of the psi's, catching minus signs or not minus signs under A cycle and B cycle shift. And we were using this placeholder nu equal 1, 2, 3, 4. Oh, I'm sorry, this is meant to be a product. And this is a complex conjugation bar and not a fraction. Thanks for asking. Yeah, so this is taking all contributions from boundary conditions, and those we do independently for left and right movers. So strictly speaking, there's 4 by 4 boundary conditions to visit altogether. But I'm lazy. I'm not even starting to track the nu equal 1 boundary condition. As stated before, this is parity odd and doesn't fit into the phase space of a 4-point function. So that's why we are only looking at nu equal 2, 3, 4. And yeah, what happens at nu equal 2, 3, 4 is that we combine the oscillator sum with the correlation function of the psi's. So all the psi's in here, and the correlation function is evaluated in the same spin structure nu as the oscillator sum is. But now, how many psis? So here again, I am sorry that I don't give a thorough discussion of vertex operators, but roughly speaking, each external state can bring up to 2 psis. So it's not coincidence that I gave this example over there with normal ordered psis. So each external state can enter through such a bilinear. And it's contracted with some polarization dependent thing. So let's say we are looking at state number 1, and there is a linearized field strength right here, which is anti-symmetrized combination of momentum and polarization vector, both of them associated with the first external state. So if I were to interpret epsilon as a gauge boson, then this is just the linearized version of doing F mu nu. And it's in particular invariant if you send the polarization to be along the momentum. And now that we're doing gravitons, we are taking double copy of that. So the graviton polarization tensor is just the outer product of epsilon left, epsilon right. So what looks like linearized gauge invariance for a chiral block is in truth linearized diffeomorphism invariant for the variance for the graviton. Okay, so what is happening here is compatible with space-time symmetries that you expect. Yeah, so this was just contribution from the first external leg, and the remaining ones will do more or less the same. They all bring their linearized field strength contracted into psi, which means there is in total 8 psis. So we need an 8-point function. Slightly scary, but we have Vic on our side, so in the end it won't be too bad. Yeah. So here I already cheated a little bit and dropped contributions that vanish. There are also terms with less than 8 insertions of psi. But spoiler, we do need at the very least 8, otherwise the spin structure sum would vanish. So more concretely, what I just used in giving that representation over there, if I had less insertions, then this spin structure sum would still give 0. This is a consequence of Riemann identities, which I'm encouraging you to look up and study. And Riemann identities were in the first place implying that the oscillator sums sum to 0. But you still get 0 if you put in a small number of psis. So if you put in 2 Sego kernels, that's not enough, it still spin sums to 0. If you put 3 Sego kernels, it's still not enough, and it still spin sums to 0. And in physical terms, this means that the 3-point function vanishes, and the 2-point function. Well, this is space-time supersymmetry in action. I guess you have seen in a variety of other supersymmetric theories that 2-point and 3-point functions can be killed as a consequence of space-time SUSY. And in string theory, this is implemented through the Riemann identities. Or this is, at the technical level, the mechanism that enforces the supersymmetry constraints on the 2-point and 3-point function. But life is tough. We are doing 4 points here. So this is for the first time where Riemann identities are not giving you a 0 dead on. So this is going to be non-zero, and the next step is to evaluate that for you. Okay. This 8-point correlator in the lowest line over there can be chopped into Sego kernels using the Wick theorem. And there are two, let me say it, topologies of how to route the arguments of the Sego kernels. So what I mean by these topologies is the Sego kernels either form a 4-cycle with respect to the marked points. This is, so to say, a connected contribution. But there could also be a disconnected contribution. So by the disconnected one, I mean product of two cycles of length 2, which is to say the square of this Sego kernel and the square of that Sego kernel. So these are the two topologies that occur. And just imagine you do this combinatorial game and go through all the possible pair contractions that are compatible with the normal ordering colons. And then half of your contributions go into the connected topology, and the other half go into the disconnected topology. And the way how you contract the fields into Sego kernels, that also determines the tensor structure for the Lorentz indices, mu, lambda, rho, and sigma. So one can immediately write down what the Lorentz tensor structure is for a given 4-cycle. Namely, it's going to be a Lorentz trace for these linearized field strengths. So this is not the trace over a space of states, but this is just tracing over Lorentz indices, those which are hanging on the linearized field strengths. Okay, and here this is just one possible routing, how to draw a cycle through the 4 points. Needless to say that there are permutations of that. So there is 2 images under the permutation group, 2 images which you can generate by cycling over 2, 3, and 4. So I refer to both the insertion points Z2, Z3, and Z4, and likewise to the linearized field strength F2, F3, and F4. So there are 3 contributions here where you match the cyclic ordering in the trace with the cycle structure of the first arguments here. Yeah, in short, there are 3 terms of connected type. Then you are probably not surprised that also in the disconnected case, there are some traces of linearized field strengths. And also there, I have 3 inequivalent permutations. So apart from the term written out, there are 2 friends that I can obtain by cycling over 2, 3, and 4. Good. Now we have an overview over the combinatorial structure. And then the leftover job is to evaluate or simplify the spin structure sum over the Sego kernels. Yes, please. Oh, yeah. Here I was still tracking it, and over there I've been lazy. Yeah, Z1 is 0 throughout. Yeah, okay. Okay, and yeah, this is once more a case for the Riemann identities. I feel more and more guilty each time I mention them without having spelled them out. But there should be a little bit of research homework for the audience. So Riemann identities imply, in this case, that this spin structure sum over 4 Sego kernels and 1 oscillator sum. So now here in the 4-point case, there's enough structure that it's non-zero, but it's non-zero in a pretty modest way. It's 1. So maybe here you can see why I normalized the oscillator sums the way I did. Yeah, all the noise coming from 4 Siegel kernels and various theta functions inside the Z nu, it all conspires to 1. So this is a tremendous cancellation between fermionic and bosonic oscillators. So it's once again space-time supersymmetry at work in the end of the day, but this time space-time SUSY is not leaving behind a 0, but it's simplifying a more complicated thing to be 1. And of course, this is not only working for the connected topology, but there are special cases of the above identity to also get 1 for the disconnected case. Yeah, very nice. So roughly speaking, you just ignore everything that has an explicit dependence on nu. And when the dust settles, we can evaluate these chiral blocks C to be constants. So once more, the RNS formalism is sometimes bashed for camouflaging space-time supersymmetry, but it's manifested here by means of the spin structure sums. If you have enough machinery to perform and simplify the spin structure sums, then you see space-time supersymmetry relating different states in the loop. Okay, so here concretely, this chiral block defined above, when you insert the results 1 and 1 of the spin structure sums, all you are left with is the Lorentz traces over the linearized field strengths. Namely, you have single traces, and this is one of the few cases where I'm cautious about factors like minus 1 over quarter, minus 1 over 4. This factor is quite important to satisfy certain ward identities. And yeah, this combination of single traces and double traces has a nickname. This is the T8 tensor, I think introduced in the Green-Schwarz-Witten textbooks and used in many places of the amplitudes literature. And yeah, what is really nice that there is no more dependence on Z and tau. I mean, we started out by saying, let's put everything related to psi into these C's. But given that the Riemann identities were simplifying things so much, it's a fake dependence on Z and tau. It's in fact, yeah, just independent on the moduli. Ooh, okay, I should wrap up. Yeah, so I think I'm 4 or 5 lines in my notes away from writing out the final answer. So we have 2 chiral blocks, C and C bar. So for each external state, there are 2 factors of linearized field strengths. And we can view these outer products of F and another F as a linearized Riemann tensor. So for each external state, say the ith one, we have linearized Riemann tensors given by the Fi involving one momentum and a polarization vector, and yet another F with one more momentum and another polarization vector. And if you really want to, you can even pick up the B field and dilaton components. So strictly speaking, this is covering the entire Neveu-Schwarz sector. But I can no longer call it Riemann tensor if I commit to B fields and dilatons. So let's just say this is, among other things, computing the 4 graviton amplitude. Yeah, and the final form, following from all the discussion here, is the following. the 4.1 loop amplitude after some simplifications. It depends on the external states through T8 tensors, each chiral block bringing one T8 tensor. So it's in total T8, T8 acting on these linearized Riemann tensors, one for each state. So there are 16 Lorentz indices that are getting contracted and that I'm taking the liberty to compress like that. And now we are done with the external state dependence. So already this is remarkable that all the states go out and multiply a single scalar integral. It's not an easy one, but it's remarkable that it's only one scalar integral and not a big collection thereof. Yeah, and as remarked before, I'm combining all the inverse in tau factors to render the integration measures modular invariant. So here's a modular invariant integration measure for tau. I'm introducing here a separate symbol for the leftover integrals over the marked points. Those, as above, are integrated over the torus, and each time with a modular invariant measure, d square z over in tau. And yeah, the non-trivial dependence on the moduli enters through this exponential of Green's functions, also known as the Kober-Nielsen factor. Okay. Yeah, so the basic principle of modular invariance is satisfied. Both the measures are modular invariant and the Green's function is modular invariant. And we will in the next lecture talk about methods to evaluate that, at least in the beginning of next lecture. There we will identify so-called modular graph forms in performing the Z integrals order by order in alpha prime. Yeah, and historically, this simple result was for the first time obtained in '82, a famous paper by Green, Schwarz, and Brink. And not only did they evaluate the 4-point string amplitude at one loop, they also took the field theory limit alpha prime to 0 and were the first ones to get the loop amplitudes of n equal 4 super Young-Mills and n equal 8 super gravity. So this is also very interesting for our friends in field theory amplitudeology, that you get a very simple result for the respective 4-point functions, namely that there's just scalar box integrals in n equal 4 super Young-Mills at one loop and n equal 8 super gravity. No triangles, no bubbles. I mean, it's so much simpler than what a naive Feynman rule attempt could give you. So this is one example how worldsheet methods also have a great deal of simplification for field theory amplitudes. And yeah, Green, Schwarz, Brink even demonstrated that you get the box integral in any number of space-time dimensions 10 and below, because they also had under control how the partition function changes if you compactify on torus. Okay, then I should really stop here.